In the perplexing realm of quantum mechanics, few phenomena are as baffling and intriguing as quantum entanglement. This bizarre phenomenon, which Albert Einstein famously dubbed spooky action at a distance, has puzzled scientists and philosophers alike for nearly a century. Imagine two particles, separated by vast distances, instantaneously influencing each other's behavior. This is the essence of quantum entanglement, a concept that seems to defy our everyday understanding of space and time. Einstein, despite his pivotal role in shaping modern physics, remained deeply skeptical of quantum entanglement throughout his life. He found the idea of particles influencing each other instantaneously across vast distances deeply unsettling, as it seemed to contradict his theory of special relativity, which stated that nothing, not even information, could travel faster than the speed of light. His skepticism, however, fueled decades of research and debate, ultimately leading to a deeper understanding of the quantum world. At its core, quantum entanglement is a phenomenon where two or more particles become correlated, even when separated by large distances. This means that the properties of one particle are directly connected to the properties of another, no matter how far apart they are in the universe. This correlation is so strong that the state of one particle instantaneously influences the state of the other, regardless of the distance between them. It's as if the particles share a hidden communication channel that defies the conventional limits of space and time. Imagine two coins, flipped simultaneously, always landing on the same side, even if one coin were on Earth and the other on Mars. This analogy helps to illustrate the seemingly magical connection between entangled particles, where the outcome of one coin flip is always mirrored by the other, no matter the distance. This, in essence, is the perplexing nature of quantum entanglement. It defies our everyday experiences and challenges our understanding of how the universe operates on a fundamental level. To understand this bizarre connection, we must venture into the subatomic realm, where the classical laws of physics break down, and the counterintuitive rules of quantum mechanics reign supreme. Here, particles behave in ways that are completely alien to our macroscopic world. In this strange world, particles do not behave like tiny billiard balls, but rather exist in a superposition of states, meaning they can be in multiple states simultaneously until measured. This superposition is a key feature of quantum mechanics and is crucial to understanding entanglement. When two particles become entangled, their fates become intertwined. This means that any action performed on one particle will have an immediate effect on the other, no matter the distance separating them. Measuring the state of one particle instantly determines the state of the other, no matter how far apart they are. This instantaneous connection is what makes quantum entanglement so fascinating and mysterious. This spooky action at a distance, as Einstein called it, challenges our classical understanding of locality, where objects are only influenced by their immediate surroundings. Quantum entanglement suggests that the universe is far more interconnected than we ever imagined, with particles maintaining a deep and instantaneous connection across vast distances. The implications of quantum entanglement are profound, not just for our understanding of the universe, but also for practical applications. Quantum entanglement is the foundation for emerging technologies like quantum computing and quantum cryptography, which promise to revolutionize how we process information and secure communications. As scientists continue to explore and harness the power of quantum entanglement, we may unlock new possibilities that were once thought to be the realm of science fiction. The journey into the quantum world is just beginning, and it holds the potential to transform our technological landscape in unimaginable ways. The quantum world, the domain of atoms and subatomic particles, operates by rules drastically different from our everyday experiences. It's a realm where the usual laws of physics seem to bend and twist, revealing a universe that is both fascinating and perplexing. In this realm, particles like electrons and photons don't behave like miniature billiard balls, but rather exist in a haze of probability, occupying multiple states simultaneously. They defy our conventional understanding, appearing to be in many places at once, and only settling into a single state when observed. This counterintuitive concept is known as superposition. It's a fundamental principle of quantum mechanics that allows particles to be in a combination of all possible states at the same time. Imagine a spinning coin that's both heads and tails at the same time until you stop it and observe its state. This analogy helps us grasp the strange nature of superposition, where a particle's state is not determined until it is measured. That's the essence of superposition. It's a phenomenon that challenges our classical view of reality, suggesting that the universe is far more complex and interconnected than we ever imagined. This fuzziness of reality extends to properties like a particle's position, momentum, and spin. These properties are not fixed, but exist in a state of flux, influenced by the act of measurement itself. Before measurement, these properties are not well defined, but exist as a range of possibilities. The wave function, a mathematical description of the quantum state, encapsulates all these potentialities. It's only upon measurement that the particle chooses a specific state, collapsing the wave function that described its multiple potentialities. This process, known as wave function collapse, is a cornerstone of quantum mechanics. This inherent uncertainty is not due to limitations in our measurement tools, but rather a fundamental aspect of the quantum world. It suggests that at a fundamental level, nature is inherently probabilistic. It's like the universe itself plays dice, with the outcome of a measurement determined at the moment of observation. This randomness is a key feature of quantum mechanics, introducing an element of unpredictability into the fabric of reality. This probabilistic nature of reality is one of the most profound and unsettling aspects of quantum mechanics, challenging our classical intuitions about how the world works. It forces us to rethink our understanding of the universe, opening up a realm of possibilities that are both exciting and mysterious. Another fascinating aspect of the quantum world is entanglement, where particles become interconnected in such a way that the state of one instantly influences the state of another, no matter the distance between them. This phenomenon further underscores the interconnectedness and complexity of the quantum realm. The principles of quantum mechanics are not just theoretical, they have practical applications too. Quantum computing, for instance, leverages superposition and entanglement to perform computations at speeds unimaginable with classical computers, heralding a new era of technological advancement. As we continue to explore and understand the quantum world, we unlock new possibilities that could revolutionize technology, medicine, and our understanding of the universe itself. The journey into this realm of possibilities is just beginning, and the potential is boundless. Section 4. Challenging Einstein, the EPR Paradox. In 1935, Albert Einstein, along with Boris Podolsky and Nathan Rosen, proposed a thought experiment that aimed to expose the supposed incompleteness of quantum mechanics. This experiment was designed to challenge the prevailing Copenhagen interpretation of quantum mechanics, which was widely accepted at the time. This thought experiment, later known as the EPR Paradox, centered around the seemingly absurd implications of quantum entanglement. Quantum entanglement is a phenomenon where two or more particles become interconnected in such a way that the state of one particle instantaneously influences the state of the other, no matter how far apart they are. The EPR paradox argued that if quantum mechanics were a complete description of reality, then it would lead to spooky action at a distance. This term, coined by Einstein, referred to the idea that particles could affect each other instantaneously over vast distances, seemingly violating the speed of light limits set by relativity. Einstein and his colleagues believed this violated the principle of locality, a cornerstone of classical physics, which states that an object can only be influenced by its immediate surroundings. According to classical physics, information or influence cannot travel faster than the speed of light, ensuring that distant objects remain independent unless connected by a signal or force. The paradox highlighted a fundamental conflict between quantum mechanics and our classical intuitions about the world. While classical physics relies on deterministic laws and local interactions, quantum mechanics introduces probabilities and non-local effects that challenge our conventional understanding. It suggested that either quantum mechanics was incomplete, missing some hidden variables that would restore locality, or that our understanding of reality needed to be fundamentally revised. Hidden variable theories propose that underlying unobservable factors determine the outcomes of quantum measurements, preserving the principle of locality. Alternatively, the act of measurement on one entangled particle instantaneously affected the state of the other, regardless of the distance between them. This idea, known as non-locality, implies that entangled particles share a connection that transcends space and time, defying classical explanations. The EPR paradox sparked decades of debate and inspired new theoretical and experimental investigations into the foundations of quantum mechanics. Researchers sought to test the predictions of quantum mechanics and explore the nature of entanglement through increasingly sophisticated experiments. It highlighted the profound strangeness of quantum entanglement and its implications for our understanding of reality. The EPR paradox remains a central topic in the philosophy of physics, prompting ongoing discussions about the nature of reality, the limits of human knowledge, and the true nature of the quantum world. Section 5. Bell's Theorem, a turning point. In 1964, physicist John Bell made a groundbreaking contribution to the debate surrounding quantum entanglement with his famous theorem. Bell's theorem provided a way to experimentally test the predictions of quantum mechanics against those of local realism, the worldview championed by Einstein and his colleagues. Bell derived a set of inequalities that would hold true if local realism were valid, meaning that hidden variables governed the behavior of entangled particles. However, if quantum mechanics was correct, these inequalities could be violated. Bell's theorem transformed the debate about quantum entanglement from a philosophical quagmire into an experimental question. It offered a definitive way to determine whether the spooky action at a distance predicted by quantum mechanics was real or merely an artifact of an incomplete theory. With Bell's theorem in hand, physicists had a clear path to experimentally test the foundations of quantum mechanics and potentially prove or disprove Einstein's skepticism about entanglement. The stage was set for a series of groundbreaking experiments that would reshape our understanding of the quantum world.